Thank you so much. Thanks for coming back. So I'll just quickly review what we covered in the previous 3 hours. So we covered the idea that in quantum field theory, line defects and line operators are interchangeable as a terminology because you can think about it as either as changing the Hilbert space and changing the vacuum, or it's extended in time, or you can think about it as an extended operator acting at a given moment in time, which is just an operator on the Hilbert space then, on the original Hilbert space, acting on the original states. Okay, then a line operator can be conformal. That means that it preserves an SL2R times SOD minus 1 subgroup of the conformal group, but the SOD minus 1 is not mandatory. There are also conformal line defects that are not invariant under transverse rotations. So you could only, this is the more important piece, or I guess I should put the other one in parentheses. This is the more important piece. Then we discussed RG flows on lines. We discussed the G theorem, which is a general monotonicity theorem for RG flows on line defects. And we discussed the connection to entanglement entropy. Okay, so these are the 4 topics we covered before. I would like to emphasize 2 points that came up in discussions with students. One actually was Erez, who might be here. He brought up a point that I believe is not in the literature. So when I told you yesterday that the G function defined as the path integral of the Euclidean line defect on a circle, a Euclidean circle defect, I told you that people have proven that this is the same as the entanglement entropy of an impurity inside the ball, roughly speaking. So this is the entanglement entropy of this region. That correspondence, it turns out from this conversation we had briefly yesterday, is correct only if there is a unique bulk, if there is a unique vacuum in the presence of the impurity. So in the presence of the impurity, there must be only one vacuum. It's easy to construct counterexamples to this correspondence otherwise. So this raises some interesting questions because there are some times in RG flows the number of vacua could change in some limits of coupling constant space. So I believe there is something to be understood. But clearly this correspondence of Cassini, Lazar, Vandea, and all these people is only correct when there is only one bulk vacuum in the present, only one vacuum in the presence of the defect. So just a comment about yesterday. Another comment is that I was asked about the holographic interpretation of this monotonicity theorem. So actually this wasn't yet understood. This is not understood yet in the literature. It was not there are various G theorems that you can see in holography, but they are not the correct one. They are not the one that's actually correct in any field theory in any number of dimensions. There are like other formulas that only are true in large and 2-derivative gravity. But the correct one was not yet understood. So it's another open question. These 2 issues are open. Today I'll discuss first the pedagogical example of a line defect in free field theory where you exponentiate a scalar. Then I'll discuss the same line defect in the ON model. That's what condensed matter physicists call the pinning field. And this is a striking application of the G theorem because for many years it was an open question and the G theorem resolved one outstanding question. And now it's also verified in Monte Carlo. I'll mention the results soon. And then I'll go to what you might call Kondo in higher dimensions. So the Kondo effect is not very familiar maybe to high energy physics, but Kondo effect is what started quantum field theory. Like Wilson understood the RG. It's the first example of asymptotic freedom on a line defect. It led to integrability and many other things. So, but there is an analog of Kondo in higher dimensions that I'll talk about today when the bulk is a free field theory. And it's a very interesting non-trivial problem. So this is my plan today. And tomorrow we'll do Wilson lines and on Sunday we'll do Wilson lines and 't Hooft lines and S-duality. Are there any more questions before I begin? The pedagogical example of a free field with a line defect of that sort.
Zohar, you might also tell everyone that you and Nadia are going to do the tutorial
Today, on Sunday, I'm doing the Sunday tutorial.
And that can't do it today.
No, yeah, Eliezer assigned me on Sunday. Yeah. So I'll do the Sunday tutorial. But anyway, I'm here to answer questions after the talk or during lunch and so on. Okay, so yesterday I gave you a problem to play with this model. I hope you had a chance. And today I'll give you the solution and also cover some aspects of this model. I know that I'm competing with a huge demonstration outside, so thanks for being here. It was not easy to park today, though. So we're going to discuss free field theory in these space-time dimensions. So now it's Euclidean signature. I'm going to analyze this line defect in Euclidean signature. We have a single scalar field. What could be simpler? So this is the simplest bulk conformal field theory. Phi is a single scalar field, and we're going to analyze some line defects in free field theory. So condensed matter people call it line defects in mean field theory. We'll do line defects in conformal field theory. Now this model, it's a nice conformal field theory, but it has it has an issue that you need to be aware of, which is that it has multiple vacua. Maybe you heard that also n equals 4 super-Yang-Mills has the same phenomenon, and many other supersymmetric gauge theories have multiple bulk vacua. So if you think about it in RD, Euclidean RD, you have to choose a superselection sector just to define the bulk physics. And you remember that in the introduction, in this material, when we covered this material, we were most interested in the situation that the vacuum without defect preserves conformal invariance, namely SOD, SOD plus 1, 1. So similarly, today and also tomorrow when we discuss Wilson lines in conformal super-Yang-Mills theory, I will be working in the conformally invariant vacuum. So I'm going to choose, basically it amounts to choosing at infinity. So this is like infinity in Euclidean signature. Phi equals 0 as a boundary condition. It's like a Dirichlet boundary condition. That's how we choose the superselection sector. We just choose phi as infinity. Yeah? Any questions? Okay, so so that forces this system to be in the conformally invariant vacuum in the absence of a line defect. And we're going to maintain these boundary conditions throughout. You just imagine in a spin system, you just force the spins to be pointing up, to be in a symmetric state at the boundary, Dirichlet boundary conditions. Okay? So now we introduce a line defect. A line defect is an integral over a world line with some new coupling constant gamma. The world line is parameterized by some parameter sigma. And then I'm integrating the bulk field over x, which is a function of sigma, over some curve C. So now we have some line defect in Euclidean signature on the curve C. And there are these asymptotic boundary conditions that fix the vacuum in moduli space of vacua. Yes?
So if you solve with a free theory, it's not only conformal, there are in fact infinitely many conserved charges for free theory.
Yes. The free field theory has many peculiarities. Also, phi equals 0 is not the only conformal vacuum because, I mean, it doesn't care if phi is 5 or 6. But think about n equals 4. Like, there is one point in modular space which is a conformal vacuum, and linearly realized conformal symmetry vacuum. So I'm in the analog of that here. I'm just fixing phi into infinity.
Okay, but the point is, once you introduce a defect, you kill all these many symmetry.
No. But you see, the defect may preserve SL2R. We're going to study that question. It might, of course, if it's a random curve, it might break many symmetries. But I'll be interested in straight defects, circular defects, and they could preserve a big subgroup.
Some of these.
Yeah, like we did in the general analysis.
Right.
It does break a lot of the symmetries, but not all of them. Okay, so this is the problem. It's a free field theory, and you have to solve. So we solved the Green's function. Yeah, we just solved the Green's function, or the equation of motion more precisely. We solved the equation of motion for the system, and the solution is probably something you worked. This is the classical solution. We have to study then fluctuations around the saddle point, but the classical solution is minus gamma over d minus 2. Then there is the famous prefactor coming from the volume of the sphere. And then we just integrate over the affine parameter on the line defect with 1 over x minus x sigma. This is phi at position x. And this is a terrible notation. I'm sorry. So x is fixed. Is that clear what I mean? This is the distance from the point where you want to measure phi to a point parameterized by sigma on the curve. Okay, so hopefully this notation is intelligible. D minus 2. So nice. This is the formula. And this omega d minus 1 is 2 pi d over 2 gamma d over 2. Okay, this is the formula for the classical solution. And now suppose you want to compute a partition function on some generic curve. So how do we compute partition function? We must plug the classical solution. We must study the fluctuations around the classical solution and then normalize by the vacuum fluctuations. So if our mission is to compute log z with the defect divided by log z without the defect, we have to do this procedure that I just mentioned. Now notice that in this classical solution, it is implicit that I've imposed boundary conditions at infinity where phi is 0. Why? Because there are actually many solutions to the equations of motion. I could have added a constant here corresponding to a different boundary condition at infinity. But by writing this formula, I'm compatible with this superselection sector. Okay? So the reason this problem is easy is that you don't have to worry about the fluctuations and the determinant of the fluctuations. And the reason is that if you plug that classical solution into the action and expanding fluctuations, the fluctuations only come from this guy, and they don't see the defect. The linear term cancels out, and they don't even see that there is a defect. So the fluctuations are the same as the fluctuations in the trivia line. Is that clear?
So can you repeat that argument, please?
Since it's a quadratic theory, the propagator of the fluctuations does not see the classical solution. Is that clear or not so much?
The determinant just comes with a quadratic piece.
Yeah, so when you expand phi equals phi classical plus delta phi, and you plug it in here, the linear piece in delta phi would cancel out by virtue of the equations of motion, and the quadratic piece in delta phi does not see the classical profile, which is a complicated profile. So therefore, this problem is easy because we don't have to worry about the determinant of fluctuations. So we can write down a closed formula for this. And for the case of the circle, I'm just going to write it for the case of a circle of radius r. So it's a circle of radius r. Let me just write the final answer. And there's a lot of analysis to be done with this answer. So it's pi gamma squared, the radius 4 minus d, then d minus 2 times omega d minus 1. And then there is an integral from 0 to 2 pi coming from this classical solution, d phi 1 over 4 sine squared phi over 2. And this is raised to the power d over 2 minus 1. Now, this integral can be done. So I'm soon coming to the main physical point of whether this line defect is actually meaningful or not. So let's just do the integral and then analyze the answer. Any questions about this? It's not.
Is this defect conformal at any direction?
Well, that's what I'm coming to. I'm coming to the question of whether this destabilizes the vacuum. You know, like in 2 dimensions, when you put Dirichlet boundary conditions, it's not good because correlators grow logarithmically, remember? So we're going to come to these questions, but you have to bear with me with the computation, and then we'll analyze the answer, okay? So we get pi gamma squared r to the power 4 minus d, and then there is a bunch of gamma functions from doing this integral. So the physics will come very soon. I'm just doing the integral. So this is one result that now I'm going to apply the operator 1 minus r over ddr. Why am I applying this operator? Can somebody remind me? Why do we want to apply this operator to the partition function? Yeah, to get rid of the UV linear divergence, which is just a mass renormalization. Okay, so this just leads to the entropy. So now we have a formula for the entropy of the defect, pi gamma squared r to the power 4 minus d times some coefficient, which is d dependent. It's a bunch of gamma functions. And this coefficient, c of d, has the following behavior as a function of d. So in 3 dimensions, it's some negative number. This is going to be 3. This is going to be 3.5. This is going to be 4. So it looks roughly like this. So it's negative in 3. It's negative in 3.5. And it's exactly vanishing in 4. Okay, this is one piece of the physics, and now the other thing is the one-point function. I want to tell you about the one-point function away from the defect. Yeah.
You don't also have to separate phases for d equals 2 circuit?
D equals 2?
Yeah.
Yeah, these computations, right, these computations are for d bigger than 2.
Yeah, so for d equals 2 you have to.
Yeah, I have to discuss it separately. For d equals 2, actually, it doesn't make sense to impose Dirichlet boundary conditions because of bulk fluctuations. So that's why I'm setting d bigger than 2. But you'll see that actually, also for d equals 3, there will be an issue. So there is some interesting physics here. But I'm just trying to write all the simple formulas, and then now I'll write the one-point function for a straight defect. So now we have a straight defect of that sort. And we're just measuring the one-point function distance x away. And what we find is gamma over x to the power d minus 3. Okay, so now I have to, and for d equals 3, for the special case of d equals 3, it's proportional. There is some gamma function. For d equals 3, you get gamma times the log of x. Okay, okay, so this finishes the simple formulas.
So for the straight thing, you're really taking now R to infinity.
Yeah, you could obtain this answer from this formula when you take the radius to be very large and x to be far from the circle. Let's say x equals 0. Yeah, you could do that, or you could just take a curve, which is just infinite straight line. It doesn't matter, it gives the same answer. So, okay, so now I have to, let's analyze the physical meaning of this story. So let's begin from the one-point function because it's the easiest to interpret. Remember a crucial thing that I told you, which is that the operator, if a defect preserves SL2R symmetry, the one-point function of any operator ought to be of the form AI over x to the power delta OI. This ought to be the answer for an SL2R preserving defect, because this sets the scale, and this is just a numerical coefficient. Remember also that the dimension of a free field in d dimensions is d over 2 minus 1. So you right away see a discrepancy. This is not compatible with this, right? Because this power is not d over 2 minus 1. Furthermore, gamma is dimensionful. That's why this formula makes sense. In our line defect, which was an exponential, our line defect was an exponential of gamma phi. Gamma was dimensionful in general dimensions. It has dimension d over 2 plus 1. It has dimension minus d over 2 plus 2. Yeah, 2 minus d over 2. So it's dimensionful in general dimensions. And it doesn't go away. So this formula is clearly incompatible with this formula. And furthermore, in 3 dimensions, it grows with the distance. So in 3 space-time dimensions, this defect just makes no sense. Setting Dirichlet boundary conditions is incompatible with the physics. So what is the physical explanation? It's a little bit like saying that you've introduced a magnetic field on at one point on the lattice, but it it made some waves propagate to infinity, and you have to then sum over all the possible superselection sectors. So it's a little bit like, I think about it a little bit like Coleman's theorem for the absence of free fields in 2 dimensions. So here the statement is that a line defect of that sort in 2 + 1 causes the vacuum an instability. Okay?
Same thing for brains, 4 dimensions, 2 brains.
Yeah, probably the same thing for a brain in 4D, probably. I didn't check. Okay? Yes?
But you can change the boundary condition to be non-zero and then.
Yeah, so you could try to quantize the free field in a different way with non-Dirichlet boundary conditions. I haven't tried. To me, this just means that this line defect creates a half-off infinity. It doesn't really decouple at infinity, like a normal line defect should just, SL2R invariant line defect should just go away at infinity. It should just decay. This doesn't, so in 2 + 1 it's clearly problematic.
It's like maximum theory.
You could think about your own analogy. However, another signature of the same disaster is in this formula for the defect entropy. If you plug d = 3 and you go to infinite radius, then the defect entropy goes to -infinity because it's negative here. That's why I gave you this plot. So the defect entropy goes to -infinity in the infrared. So that means that the quantum dimension, so to speak, is arbitrarily close to 0, and the flow never stops. You never reach a constant defect entropy in the infrared. So this is another signature that this is just a never-ending RG flow, which destabilizes the vacuum, and this system never reaches a conformal defect in 3 dimensions. So this is actually a counterexample to the fact that the infrared is a conformal defect. It's not. But I strongly believe that this is a sickness of just free filtering. It's known experimentally that as soon as you add a 5⁴ interaction, this flow stops, you get a finite defect entropy, and I'll actually quote the answers for 5⁴ theory. But in free filter, it seems very sick.
Can I ask? If I would do a Hamiltonian formulation, would I find there is no vacuum?
I don't. If you set phi = 0 boundary conditions, you'll find exactly what I said. You have to set boundary conditions. So if you solve with Lagrangian, Hamiltonian, I don't think it matters.
No, how would I see the instability? Would I see there one possibility there is no ground state?
My interpretation is that the boundary condition phi = 0 makes no sense.
And therefore we cannot preserve SL2R.
But in the Hamiltonian language, you're adding phi at one point times delta function to the
Yeah.
Hamiltonian.
Yeah. So then there.
Too much
Yeah.
perturbation.
It's a huge. That's what the kid said. This perturbation is just too strong in 2 + 1.
What
Yeah.
type of entropy are you calculating here?
This is the defect entropy.
Entanglement.
Defect entropy.
What does it mean?
That's what I defined in the previous. It's the circular expectation value of a circular loop. Okay.
And in 4 dimensions?
No. So now I'm discussing 4 dimensions. So in 2 + 1, it's sick. It's known to be sick. I think everybody agrees that this is sick. But in 4 dimensions, it's perfectly okay. Amazingly, it's perfectly okay. Why? So there are various ways to say it. One is that this power exactly coincides with this power because d over 2 - 1 is 1, and also this is 1.
It's only at d = 4.
Hmm?
It's only at d = 4.
Only at d = 4. So at d = 4, it's an actual SL2R invariant conformal defect, and the vacuum is perfectly fine, but only at d = 4. And what happens to the defect entropy?
0.
Exactly 0. And what did I tell you yesterday? If you have an exactly marginal parameter on the line defect, because this is a monotone of the RG flow, this has to be independent of the exactly marginal parameter. And indeed, miraculously, this vanishes and the gamma dependence goes away. So in 4 dimensions, the correct interpretation is that gamma is an exactly marginal parameter. It affects the 2 1-point functions, 2-point functions. It doesn't affect the defect entropy, and it's an SL2R invariant defect. So let me just summarize what I view is the answer for this model. So in d = 4, it's an SL2R invariant defect with gamma exactly marginal. And for d = 3, there is an instability of the Coleman type. There is an instability of the Coleman type. Okay.
Although if you will do phi squared in d equal to 3,
Phi squared, as I said yesterday, flows to a trivial defect. It flows to an SL2R invariant trivial
it's
defect.
not really marginal.
It is marginally irrelevant. This computation is in some appendix of the paper I wrote for phi squared. Okay?
So if you add another defect to the opposite charge, that goes
This is a real number, you see? This is a real number, it's not I. In Euclidean signature, the action has no I's. So you're not going to save it in any way. Oh, you're saying that with the opposite, with minus gamma, not opposite.
Yeah, minus gamma.
Okay, so if you, okay, let me think about that. So the answer would then be, because of the superposition principle, minus gamma over x minus x now d to minus 3. Well, it's possibly an interesting idea. Possibly an interesting idea. It does cancel the leading piece.
This is what saves things in Maxwell.
Possibly an interesting. No, Maxwell is fine in 4 dimensions. Okay.
It's a string of dipoles.
Yeah. I understand the idea. It's possibly an interesting idea. You can go and study it. I'm going to focus on a single defect, because also, I mean, there's lots of experimental data about this, the interacting version of this thing. Okay. So, are there any questions about the statement? This is the simplest toy model for a conformal defect in 4 dimensions. What, 5 dimensions? No, in 5 dimensions, this would be a problematic thing to try because it would be an irrelevant deformation on the line, and you see that C becomes positive, and the defect entropy is not monotonically decreasing, which signifies that you're going to the UV rather than to the infrared.
Taking these 2 defects, you cannot think about it, the limit.
Yeah, you can fuse them and get a trivial defect, yes. Yeah, so if you want, I can make a wild guess. If you take these 2 defects, they will fuse to the trivial defect, which is conformal, plus, I think, plus possibly, I'm not sure, the phi squared defect. You might get also the phi squared defect in the sum of the fusion, and that is marginally irrelevant. So perhaps the right interpretation of this system with 2 defects would be a trivial defect, but it's just a wild guess.
This is not a problem for a compact building.
Yeah, it's just 2 parallel infinite lines.
Right.
We're talking about 2 parallel infinite lines, yeah. Okay. Yeah, I think you ought to get a trivial defect, that's my guess. Just because the fusion will have to contain the trivial defect plus ones that are, I know, are marginally irrelevant. So it has to be checked though.
But what if you integrate along the line, let's say, square root of a normal derivative to the line, or acting on phi, so some fractional derivative?
Yeah, Nikita is asking about maybe exponential of I, maybe d phi to some fractional power, dt. Yeah, I mean, this is not...
No, the fractional power of the derivative.
Yeah, okay, fractional power derivative. I don't know, these are not usually considered because it's not very local. So I don't know what to do with this.
I have a question.
Yeah.
So let space be compact.
Yeah.
We don't have to discuss the boundary conditions.
Correct.
And the whole conformal symmetry works as it could. So say it's a big sphere.
Yeah.
And I put 2 of these defects with opposite charges. So the question I'm trying to do is track the U1 symmetry that shifts phi.
Yeah.
It's the R symmetry that shifts phi by the constant.
Yeah.
Then if I do that, then I don't see how it flows to the phi squared defect.
You're right. The phi squared is forbidden by the R symmetry arguments. You're saying you'll just get a trivial defect in the
R in the
infrared.
sense of real numbers.
Yes, I see.
Yeah.
Yeah, my guess stands it's a trivial defect, but I don't know the details when you have a pair of them. Nati gave an argument that phi squared cannot appear, and the argument sounds right from the shift symmetry. So it's going to be trivial, that's my guess. You have to check it though.
We're calculating the entropy for the case of finite radius.
Yes.
But on a sphere, you will integrate over the biplane.
Yes.
But then it's
Yes, all of this is all true. Okay, now I'll tell you the more interesting case. Of course, people are more interested in what happens when you have the ON Wilson-Fisher model, in which there are n fields, and you're tuned to the fixed point, right? I don't want to discuss the off-critical ON model. I'll just discuss the critical ON. This is called the ON Wilson-Fisher model. It's a fixed point in any number of dimensions above 2, smaller or equal to 4. It's free in 4 dimensions, but otherwise it's an interacting fixed point. And phi A stands for phi 1 all the way to phi n. Okay, so this model has various lattice realizations, but regardless of that, you are allowed to consider the line defect that we just studied, namely the exponential of a phi 1, gamma phi 1 dt. I just chose 1 inside ON because that's the direction in which you turn on an external magnetic field. So you break the rotational symmetry explicitly on the defect. Now, to find this is called in condensed matter the pinning field, and there are lots of experiments on this system. There is a beautiful review by Wojta from Dresden, recent review on this field. There's lots of data. And this flows to a conformal defect, it is believed, in any number of dimensions between 2 and 4. That's what we see in Monte Carlo. So this problem with the instability in 3 dimensions for the free field is avoided because we have phi to the 4. And the phi to the 4 stops the growth of the field outside of the defect. It stops the instability. So we believe, it's believed that this flows to a conformal defect. And the G theorem has a striking application for this case because it actually proves it. It proves that the infrared cannot be trivial. So gamma is a relevant perturbation at gamma equals 0. So if you start from gamma equals to 0, which is the case where no external magnetic field is present, localized external magnetic field, you add this perturbation, it's relevant on the line defect because the dimension of the order parameter in the ON model is like half in 3 dimensions. It's close to a half. It's always smaller than 1. In any, for this whole region, the dimension of phi 1 is smaller than 1. We know it from statistical physics. So it's a relevant perturbation. And therefore, the G theorem immediately means that the G of the infrared has to be smaller than 1, while the G of the UV is 1. So this immediately proves that the infrared of the system cannot be trivial, because the trivial line defect has G equals 1. So the infrared has to be a non-trivial line defect. And indeed, that's what we see. So how can you say anything about the system? So what you can do analytically is not a huge amount. It's interacting in the end of the day. But you can do, I'll show you the results that are currently known and tell you what the open questions are. So people have been able to solve this in the epsilon expansion, of course. You can find the fixed points of the system in the epsilon expansion because it's a weakly relevant perturbation of the trivial defect. So the defect is almost free in 3.99 dimensions. And you can set up an epsilon expansion. This was done up to 2 or 3 loops. And most recently, an exact Large-N solution was found. So it looks a little weird, but you know, this model is solvable in the Large-N limit. And it turns out that the solvability is not destroyed by this line defect. You have to find the new classical trajectory, but it was found, at least at the fixed point, at the infrared fixed point. It's not, nobody solved the full RG flow on the line defect yet, but at the fixed point of the defect, a classical solution to the ON model was found in the presence of the defect, and so many things are known exactly. So let me just give you, yes?
But even away from the defect, there's an equation.
Right, but it's nobody was able to solve it
I
yet.
understand, but that's right, there is like
what they call it, I forgot, Dyson-Schwinger equation, also away from the fixed point, but nobody was able to solve it yet. However, it was possible to guess, to find the solution at the fixed point, at the infrared fixed point. So it's like a self-consistent solution where you assume that an infrared fixed point exists. You find the classical solution, you find the fluctuations, and everything makes perfect sense.
Is the solution hard to write?
It's a little bit like what Kitaev did in the Schwinger-Dyson equations of SYK, that he just found the solution for the infrared, so to speak. So we used a similar technique and solved it in the large N limit. We used a similar technique to solve this problem, to just hunt the solution in the infrared fixed point. Yeah.
But is it easy to write down?
Yeah, it's written down explicitly in the in some papers. I'm not going to do it here. I have to introduce the whole large N technology, but yeah, there is a nonlinear Schwinger-Dyson equation with a line defect, and at the infrared fixed point, somehow we managed to guess a solution. Okay, so I'm going to give you some results from these two methods and compare to experiment, and move on to the Kondo problem. So in this problem, there is a conceptual point that is worth knowing. You remember that we had a displacement operator on the defect, and that was a protected operator of dimension 2 on the defect. It came from essentially the explicitly broken translational symmetries. Here, there are explicitly broken ON symmetries. So the defect breaks the ON symmetry to ON minus 1. So the very same logic that implies a displacement operator from the breaking of translational symmetries implies the existence of protected operators from the breaking of ON symmetry. So these are the phis with A which is not equal to 1. So the phis in the directions which are transverse to 1, they correspond to some protected operator on the defect because they come from explicit symmetry breaking. Their scaling dimensions are protected and they're exactly 1. So when you look at the numerical Monte Carlo results on this model, people see the displacement and they see these other guys. They're all called tilt operators, as I said yesterday, in condensed matter. So these are easy predictions to make.
No?
Yeah.
Protected, you mean that UV and diode are the same?
No, protected in the sense that in the infrared fixed point, nothing is known about their G flow away from the epsilon expansion. But at the infrared fixed point, you're guaranteed to have a dimension 2 displacement operator and dimension 1 tilt operators. The argument for that is the d mu. I'll just remind you quickly that there is a d hat times a delta function. And the argument for the other ones is the same. There is a phi hat a not equal to 1. And these are the ON, these are the broken currents, which are labeled by some A not equal to 1. So this is phi hat, and then we have a delta function. So it's the same argument. Okay. So these are seen. So what people are actually measuring is the dimension of phi hat 1. Because this is not protected. We don't know the dimension of this defect operator a priori. And you should expect that it's bigger than 1, because it's an infrared stable fixed point. It's the endpoint of some flow with very little symmetries. So you should expect that phi 1 in the infrared picks up a defect dimension which is bigger than 1, even though in the bulk the dimension is a half, so roughly speaking. But it has to pick up a large anomalous dimension on the defect so that the defect is a true infrared stable fixed point. So Monte Carlo, there are, from the last 2 years, there are 3 measurements. 1.60 with error 5, 1.52 with error 6, 1.40 with error 3. They are clearly not compatible with each other. But these are 3 papers from the last 2 years. They're kind of in the same ballpark. And, well, after...
Why are they compatible?
I have no idea.
No, but within the errors.
Even within the errors, they don't seem compatible. This is off.
What do they measure?
This, the dimension of the
No,
defect
how do-
operator
how-
phi 1.
How do they measure it? What do you really measure? It's Monte Carlo you were saying.
It's quantum Monte Carlo.
Okay. It's not experiment. Yeah.
It's quantum Monte Carlo. There is an experimental measurement too, with localized, but it has a huge error bar.
What's the value?
What is it?
What's the value of the number?
It's like also 1.40 something with a huge error bar of like 0.2, not 0.0, not in the second digit. But you see clearly there is some discrepancy here.
This is in 3 dimensions?
2 plus 1, yes. I'm sorry, I should have said that. This is in 2 plus 1. In 4 dimension, in 3 plus 1, these measurements are not interesting because this fixed point is free. Gamma is exactly marginal, and the fixed point is trivially solvable, like I did in the previous part of this lecture. Okay, so just to show you that theory has some applications, that you can do something with theory. So one thing you can do is use the epsilon expansion and wildly extrapolate. Another thing you can do is after you do the two-loop and Borel summation. Another is that from the exact large n solution, this is for n equals 1. I should have said that too. There are also measurements for n equals 2, 3. Another thing is you take the large n solution and wildly extrapolate. So
The larger you can use also a local thing?
maybe yes, but the holographic dual of this theory is Vasiliev theory, so I don't know. Okay, so what theory gave at the moment is 1.55 plus minus 0.14. This is from the epsilon expansion, just doing second order resummation and Borel resummation. And from the n going to infinity limit, there is an exact result. I'm not going to extrapolate it because the 1 over n corrections are not known. But there is an exact result at large n. It does not scale with n. And it's analytically known with some zeta functions. It's 1.542. But it's not bad. Okay? If you assume that there is not much variation with n, which the epsilon expansion indicates, it's not very far away. So in this model, it seems that large n is actually working much better than in QCD. It's very close. Okay, are there any questions about this defect? This is like the simplest line defect. It's not a Wilson 9, but it's still a very rich story.
Is it just a straight line?
Huh?
Is it just a straight line? You didn't discuss other configurations, right?
Right, they just do a straight line which corresponds to putting a localized magnetic field at one point on the lattice.
Can you
Just say a
perform
word
special
about these.
topological?
You said they're experimental results as well.
Yes.
Could you explain what the experiment precisely?
Yes. So in the experiment, there is. I'll just say a few words about what is the setup for n equals 1. So you can realize the n equals 1 Wilson-Fisher fixed point by a spin from a lattice of spins interacting antiferromagnetically. Then you tune the coupling constants to the fixed point. This is the first step, which you have to do numerically. Is that okay?
Do numerically.
It's a oh, sorry. You're asking about the actual experiment. So you go to the phase transition. You're tuning to the phase transition of some antiferromagnet or some material that is known to be in the Ising universality class. And then all you do is you apply an external magnetic field, but localized to some small region of space. Okay, and then you study grid functions, neutron scattering far away. And from that you can extract the dimensions of defect operators. You can extract many, whatever you want. But it has huge error bars compared to quantum Monte Carlo because it's a kind of an involved experiment. Okay. Okay, now I want to tell you about the next example of a line defect, which is actually much less trivial. But the bulk is trivial, but the line defect is complicated. So I'll go back now to this model, ddx, a half d phi squared. So there is more life in this model than just this e to the phi. There is something much more rich that you can do. So just for simplicity, I will take three fields, three free fields. So A goes from 1 to 3. So this is just 3 decoupled free fields. In this model, there is an interesting line defect, which takes the following form. So since there are 3 fields, you can think about an O3 global symmetry that rotates them. And therefore, there are matrices, SO3 or SO2 Lie algebra matrices in the game. And you can take them in any representation that you want. So let's take them in the spin S representation. So meaning these are matrices which are 2S plus 1 by 2S plus 1 matrices obeying the algebra of SU2. And now you formulate the following line defect. Again, gamma would be a coupling constant. And then you take phi A, T A. Pass order the exponential of gamma phi A T A dt, and you have to trace. Because now you get a matrix. You have to trace in the S-dimensional representation. You trace in the in the 2S plus 1 dimensional representation. If you know a little bit of the history of quantum field theory, this is the 2 plus 1 dimensional analog of the Kondo problem. So this is the 2 plus 1 dimensional analog of Kondo. Here, the bulk is completely free. So you might be shocked that it's actually not solvable, but it's not. We do not know the expectation value of the circular line exactly, even though the bulk is free. And the methods of solving this problem are limited. And there is a lot of interest in condensed matter in this problem. So now I'll first summarize the results that are known. Sorry. TA is TA are three matrices which obey the Lie algebra. And it's independent of time. The time dependency is in the quantum field.
Along this curve.
Yes, along a curve which you can call C. So it's like Wilson 9, but phi A is not a gauge field, but it's a scalar field. In Wilson 9, we are interested in tracing and all these things because of gauge invariance. Here we just want to trace because we want an SO3 invariant line operator. So what does this describe physically? How is this realized in the lab? This is realized in the lab if instead of a localized magnetic field, you put an external atom of spin S. And that's it. So you replace one line site with a spin S atom or nucleus. And now this spin S nucleus couples to the bulk in an O3 invariant fashion. And this is described by this line defect. That's why you have to trace, so that it's O3 invariant.
That atom is infinitely massive.
Yes, and the nucleus is infinitely massive. It has just some 2s plus 1 internal states. Then otherwise it has no states, just the direction of the spin. Okay, so let me tell you about this problem. Some things are known about it analytically. I'll tell you how. Some things are known experimentally. Some things are known from Monte Carlo. So what is the question? The question is, like always in QFT. In QFT, we're interested in the vacuum. Here, we're interested in the vacuum. We want to know the infrared. Clearly, gamma is a relevant operator in 2 plus 1 dimensions. It's a relevant parameter. It's marginal in 3 plus 1, but relevant in 2 plus 1. And we want to know the infrared. Is the infrared screened? Is the infrared one of those disastrous logarithmically growing defects that we saw before? Is the infrared a nice conformal defect? That's what we want to know. So it's a question about the property of the vacuum with this perturbation. So I'll just tell you what's known from theory, and then what's known from experiment and Monte Carlo. So this is going to be d equals 4. I'm just going to tell you what happens as a function of the dimension. This is just going to be 3.97 as a benchmark to see some phenomenon that I'll explain. And here at the bottom, there will be d equals 3, which is the experimentally interesting case. And here we have the spin. So I have to give you a phase diagram as a function of dimension and spin. By spin, I mean isospin. It's the representation of this matrix TA. So there is a region in this diagram where you can study this problem using analytical techniques. You can do it on a piece of paper, not with experiments. So the region looks, roughly speaking, like this. So there is some region which looks like this, where you can understand the problem analytically. And what do you see in this region? In this region, you see an interesting phase transition line that I'm going to extrapolate. We don't know what's happening here, so it's just an extrapolation. But in the region that you understand, you see a phase transition line. And just to give you some orientation, this is roughly s equals 10. And this is roughly 1/pi. So it's not an actual possible spin, it's just extrapolation. So what happens above this line? Here we have two fixed points. So actually there are two conformally invariant fixed points on that side of the line, and no fixed points on this side of the line. What do I mean by no fixed points? I mean this disastrous infrared behavior that you don't have a conformal defect. So this is the infrared catastrophe, if you want. Disaster infrared catastrophe. Okay, so this is the phase diagram. Now I'll show you how the beta function looks like. And then I'll explain how this is done. So this phase diagram follows from the following beta function. It's a beta function for the coupling gamma.
So what is the blue shaded region?
This region is where you can say something confidently using theory, piece of paper. And this region you need to do maybe simulations or.
Or what is that other dotted? Oh, I see.
So there are two fixed
What
points.
is the dotted line just picks out the 3.9.
Yeah, this is just to give you some orientation that for spin 10, this transition happens at 3.97 dimensions. It's just to give you some orientation for.
It's not really spin in space-time, it's just a representation of this OM2, right?
Please, say again, please.
Why is this same? I mean, you describe everything here in the scale of the.
What I didn't understand the question.
It's a spin of
You
the
say
impurity.
spin.
Spin? It's like in the Kondo problem. It's an isospin. It's isospin. It's SO3
Right,
representation.
Okay.
I'm just calling it spin because it's a spin of a nucleus, but you should think about it as isospin because it's an SO3 representation. Any other questions?
Is the boundary very sharp or it's like?
No, it's just I just gave you a cartoon. A cartoon. I just want to show you how can two fixed points disappear into a disaster. I want to show you how this phase transition happens in terms of a beta function. So the whole point is that in this region there is an exact solution, and you see this transition clearly, and you can analyze the disastrous region. For that you have to find an exact. There is some sort of exact beta function. I'll explain how it's found soon. So the beta function is for this coupling gamma, right? And the beta function looks like this in 4 dimensions. I'm gonna plot a bunch of lines and then tell you what they correspond to in the diagram. Okay, so let me go one by one. So this is d equals 4. This is d equals 4. So unlike the pinning field case, where we just integrated 1 phi, which was exactly marginal, here it's not exactly marginal. It's an interacting defect even in 4 dimensions. And gamma is marginally irrelevant. So there is no non-trivial fixed point in 4 dimensions, in strictly 4 dimensions. When you go slightly below, there is of course the trivial fixed point where the spin is completely decoupled. The nucleus is completely decoupled. So when I said 2 fixed points, I should have said really 3 fixed points because there is always the trivial fixed point. I meant 2 non-trivial fixed points. There is always the decoupled trivial fixed point. So there is the decoupled trivial fixed point. There is an infrared stable fixed point. And then there is another infrared unstable fixed point. So from this fixed point, you can flow to this fixed point. This one has a relevant operator, and this one does not have relevant operators. at least not ones that preserve O3. Okay? So there are two fixed points. And then at some special point, these two fixed points coincide, and then they annihilate, and there are no more fixed points, and you have a runaway to infinity. A runaway to infinity usually means, in the beta function, an instability. So this is the disaster catastrophe in the infrared, where there is no fixed point in the infrared. So this curve, let me just put labels on this curve. This curve happens to leading order when the epsilon times the spin is equal to 1/pi. So to leading order approximation in some scheme that I'll explain, when epsilon times the spin is 1/pi, this curve happens. This is the beta function when epsilon is. This is slightly bigger than 1/pi. Sorry, this is slightly smaller than 1/pi, and this is slightly bigger than 1/pi. So that's why when we do this wild extrapolation, this is 1/pi. Just because it seems to be that's the bound between two fixed points and no fixed points. So the prediction of this extrapolation here would be that for any spin, 2 + 1 dimensions, any realistic spin, there is no fixed point. It's always infrared unstable with this Coleman instability. Okay, so how this is obtained? So this fixed point is very easy to see from an epsilon expansion, but this fixed point is completely non-perturbative. So to see it, you have to do something more sophisticated, and I'm going to explain it in the last couple of minutes of this talk, and then there will be plenty of time for questions. Are there any questions about the statements here?
But why is an asymptotically free theory for you catastrophe?
Why is there?
Well, in the infrared.
What
In the
is
infrared,
there?
something happens. Okay, so
What? I didn't understand, Eliezer.
What
You
is
see
the
the-
disaster?
Why is it infrared catastrophe?
Bound state.
It's because it's like Coleman's instability.
Okay, this is, you don't view it, you don't think there is something changing in the dynamics in the infrared?
No, in the infrared, you have a free field. So in the infrared, like there is something that takes over this boundary condition into infinity. So when I say infrared catastrophe, I mean something like Coleman's logarithm.
Large fluctuations.
Large fluctuations in the infrared, yes. Yeah.
I think again you can make it sound less dramatic simply by working in a large finite volume, two defects, one of them here and one of them very far. Then there is no catastrophe.
Yes.
And then it's much less dramatic.
Yes.
It's like putting charges in compact, if you have charges in compact space, you just have to put another one very far.
Right.
And then there is no catastrophe.
But you see that here there is a subtle dependence on dimension. For
Yeah.
some dimensions there are fixed points, for some dimensions there aren't.
The same is true in the other case.
So I'm plotting this. I'm plotting the phase diagram of a single defect at the infinite volume with Dirichlet boundary conditions because that's what
yeah,
people
but
measure.
the result sounds almost impossible. But if you think of it in finite large volume with two charges, then you get the same results locally, but
Yeah.
it sounds much less dramatic.
Yeah, I think the challenge here for theory is maybe to somehow say something about this region, about which there are lots of measurements, but we cannot do it now. So I can only we can. So I'm going to explain how to.
Let me elaborate on this a little bit. Imagine you're in a system that has vortices, which are seen in the lab. So strictly speaking, the vortex is saying 2 + 1 dimensions. The vortex has infinite energy.
Mhm.
And you would say, oh, this is catastrophic. There aren't really any vortices. That's of course not the right answer. The right answer is that with the vortex here, there's an anti-vortex there.
Yeah, but
Vortices are
but it's the distinction. They're dynamical. So when you spin a system, they can create out of the blue.
Same thing.
Here, these objects are introduced by hand,
Yeah.
and you can study the response of the
Change
system.
parameters in the other theory, such as the mass of the vortex goes to
Yeah,
infinity.
but then-
you get
yeah,
it
yeah.
becomes a defect.
But a vortex is actually a special case of one of those defects. So I think it will boil down to the same statement. Are there any questions about
So
this?
you drew this beta function, and that's an exact.
I'll show you.
Calculate this.
I'll show you how it's calculated. It's exact in
Then
this
what
region.
prevents you from, what defines that region?
I'll show you now. So we came up with some analytical technique to solve this problem and to find this non-perturbative fixed point. I should say though, I should give, so this transition here, and this a special case where these two fixed points annihilate, was seen 2 months ago in Quantum Monte Carlo by Weber, Wojta, Adam Nahum, and some others. there were several papers, so I think this picture is now confirmed in quantum Monte Carlo. So I'm pretty sure it's correct. Yeah.
System can be generalized to higher groups, I guess.
Yes, I just gave you the O3 version. There is a recent paper by Max Metlitsky, Ashwin Vishwanath, Subir Sajdev, and maybe one or more people, where they studied generalizations to ON, where you put on a line defect some generically projective representation of ON. You're allowed to do that. Like symmetric tensor, and you study a version of this. O3 is the simplest case.
What happens in the larger?
Well, Max's paper has one example where they do the large N analysis. It's very similar to the spinning field. You have to find the new saddle point. So there is one case that they solved the large N limit on. There are people in condensed matter that say that the Schwinger-Dyson equations for the spinning field and this Kondo problem at large N are very similar to SYK. So people are looking at that for that reason. I'm not an expert on SYK, so I can't say to what extent this is true. Now, let me show you how you attack this problem analytically. This is a useful technique for you to know. So we have three free fields. We have three free fields, and we need to couple these free fields to the Kondo defect, which is a spin S nucleus. So writing this pass-ordered exponential with the TA matrices. Oops. Writing this exponential of a non-abelian version of this phi A is complicated. How do you put it in the action? But there is a very beautiful trick, which is you could think about it as a coadjoint orbit. But I'll just write the Lagrangian now for this SO3 coadjoint orbit, and that's actually how we analyze this problem. So how do you need to model in a Lagrangian a nucleus with spin S, isospin S. So you need to write the quantum mechanical model with degeneracy in the ground state, which is 2s plus 1 fold. So there are many ways to do it. You could write there are many ways to write a quantum mechanical model with 2s plus 1 ground states. Then on this, so on these ground states, you can then have TA matrices that are just quantum operators on the defect, and you couple them to the bulk. So now you just have to choose how do you represent 2s plus 1 degenerate ground states in the vacuum. So my favorite model is the monopole. Just put the monopole at the center of the sphere, and it leads to an exact degeneracy if the monopole has monopole charge S. Another way is the coadjoint orbit. The coadjoint orbit is basically the same as the monopole. So let me write the quantum mechanical Lagrangian. You might have seen it in school. I don't know. So it's I, Z bar, Z dot. So I'm not coupling into the bulk yet. I'm just writing the first term. So what is Z? Z is two complex variables. Z is just two complex variables with a constraint that they live on the sphere, and the radius of the sphere is 2s. These two complex variables have a gauge invariance, which is Z going to e to the I omega Z, and they are bosonic variables. So this is a quantum mechanics with only one derivative. So it only describes ground states. It has no excited states. Secondly, the target space of this quantum mechanics is the four-dimensional sphere because of this constraint, three-dimensional sphere because of this constraint, but you have a gauge symmetry, so you have to quotient by U1. So really the Z variables live on a two-dimensional sphere. And this funny action secretly introduces a monopole at the center of the sphere. So if you just quantize this if you just study this quantum mechanics in detail, you'll find that it has 2s plus 1 states. 2s plus 1 degenerate states. And now you can couple it to the bulk by introducing a parameter gamma, like we had in our Wilsonine, Z bar sigma A Z times phi A. And A summed over. And this, okay? So the claim is familiar, perhaps, to those that worked a little bit on Wilsonines, that this quantum mechanical model couples a spin S impurity to three bulk free fields. And you have to bear in mind this constraint and this gauge invariance. Okay, so that's how you put this pass-ordered exponential into the Lagrangian. You just couple 3 scalar fields to a spin S, to a quantum mechanics with 2s plus 1 ground states. Okay, and now you have to compute the beta function for this coupling. That's essentially the name of the game. So there is a technique. So the main trick of how you solve this problem and find this beta function that I plotted here is that, of course, it's an interacting model. You don't have any chance of solving it exactly because there is a cubic coupling here. And that's why it's much different from the exponential to the phi, which was a quadratic model. This model is intrinsically cubic, intrinsically interacting, so you don't have much of a chance to solve it exactly, I believe. But there is a limit, there is a double scaling limit where it's exactly solvable. So what is this double scaling limit? It's the large spin limit. So the idea is that large isospin, large S, is the limit where this model becomes classical. It's a little bit similar to the large, I think, maybe Nikita can correct me, but also in the general theory of coadjoint orbits, the large quantum number limit is a very nice classical limit. So here something similar happens, even though it's interacting with the bulk fields. So do the following rescaling. Take every scalar field in the bulk, rescale it by square root of the spin, and take these variables z and rescale them by the square root of the spin.
So basically you're saying you can couple, so your line defect depends on the path, on the sphere.
Yes. Yeah, but here the path is not specified. I just took it to be a straight line for simplicity. You could do it for any curve. You could do it for any curve. So the double scaling limit would work for any curve, and you can solve something in the large spin limit.
You mean that you just can choose any path on the sphere?
You can choose any path of what?
On the two-dimensional sphere.
What two-dimensional sphere?
The two-dimensional sphere is whose quantization gives you the representation of S. But if you don't quantize it, just take it classically. Just pick any path.
Yes. So Nikita is anticipating that this limit will be classical, and the saddle points would be some trajectories on the sphere. Maybe that's what you said? Okay. Yeah.
Why do you call it double scaling rather than scaling?
You'll see in a second, Nati. 1 second, it will come. So, after this rescaling, the action becomes S times something, and we like to have a large parameter out front because this is like 1 over h bar. S is an integer. You're asking how do we see that in this quantum mechanical model? S must be an integer for this quantum mechanical model to make sense. This is the Dirac argument from 1938. You see that these variables live on a sphere, on a two-dimensional sphere. So if you don't properly quantize the radius of the sphere, there will be a Dirac singularity at the south pole in some convention. So strictly speaking, you can quantize it with any S, but the Hilbert space would not be in a finite dimensional representation of SO3. So a finite dimensional representation and SO3 symmetry, you need to have no Dirac string. Okay, so now there is S in front of the action.
You also think of Z1 and Z2 as two harmonic oscillators. So
Yeah.
the constraint is that A1 dagger, A1 plus A2 dagger, A2 is something, but this has to be an integer because that's the spectrum.
Right. So there is S now out front. We have this guy. And then we have the defect piece. I'm not changing the names of the variables, not to create clutter. But now we have gamma, square root of S, times this coupling. So this is the key idea in this whole business of the Kondo problem. So we see S outside, but it's still pesky because there is S inside too. So what we do now is we call this gamma twiddle. And we say that we are going to solve the model in the limit of S going to infinity, gamma going to 0, with fixed gamma twiddle. I think it's called double scaling, right?
No, that's called scaling.
Scaling, sorry. We always call it double scaling in all our papers. It's called scaling because, scaling. This is a scaling limit. So it turns out that this is the right limit. Namely, if you actually study the beta functions for the original gamma, the fixed points are at order 1 over S. So in this problem becomes completely classical now in the large S limit. and the beta function becomes a property of a classical differential equation. So the classical differential equation that describes the saddle points of this model admits logarithms near the defect, and these logarithms allow you to read the non-perturbative beta function. So we have an exact non-perturbative beta function for gamma twiddle. Okay. And it's something like, just from memory, it's something like gamma twiddle squared plus 1 with some coefficients. So there is an exact non-perturbative beta function, and this leads to the phase diagram that I gave you. Obviously, it fails for small s. So unfortunately, that's why there is a region that we cannot cover with analytic techniques. But there is an exact beta function, at least in this limit. And it's a nice exercise to follow because it's a classical differential equation from which you read out the beta function. It's by logarithms in the classical differential equation. Okay, so this is the main idea in that business. Are there any questions before I move on? Yeah. No, this is the squiggly. There are this.
The relation to the picture. What is S in the calculation?
Okay.
It
So
goes to infinity.
what is what?
There is an S that goes to infinity.
Yes.
And there is an S that is finite.
No. S goes to infinity. Gamma goes to 0, such that such that gamma times square root of S are kept finite.
Yeah, but now I thought you described the solution.
He's asking to explain the boundary of the picture.
There where there is an S that is finite.
Okay. So this curve. Yeah. So this curve comes from the. So you're asking about this weird shape here, right?
I'm asking about the relation of the finite S in your x-axis in this picture and the S that already went to infinity. This should be different S.
Right. So in this double scaling limit, you see two fixed points. Sorry. In this scaling limit, you see two fixed points for in some domain, and no fixed points in some other domain. You have this. You see these beta functions, and you can see this region. That's what it allows you to cover. I had this weird shape here because there is another technique to study at fixed d the asymptotically largest limit, which I'm not going to describe today. Yeah, so you can do another, in addition to the double scaling limit, which allows you to curve out this region, another thing you can do is you can just study everything that happens past some point at fixed d at very large s. There is another simplification in that limit. Okay? That limit is always to the right of the red curve. So you do not see in that limit the two fixed points. But you see what happens, at least at d equals 3 at large s.
It's to the right of what?
So there is another limit, which is solvable, which is fixed d. And asymptotically large s, much bigger than epsilon, much bigger than 1 over epsilon, much bigger than anything. In that limit, you never see these two fixed points. It's always like here. So, and from just numerics, we saw that it begins to be somewhat accurate, this analysis at s equals 7 or 8. So that's why I had this weird shape. Okay.
So, when I asked you about the signs, you gave us a set of beta functions.
Yeah.
And all of them for large gamma went to minus infinity.
Correct.
But the formula you gave did not.
Right.
So
I just
asked,
this formula was sketchy. You can find the full formula in the paper.
Okay.
I can also work it out. It's like 10 minutes exercise. I can work it out on Sunday, the exact beta function. But anyway, the expression is in the paper.
Is it involved other kinds of functions? Or?
No, it's an elementary rational function. It's an elementary rational function which has all these phases that I showed you. Any other questions before I move on? Very good. I haven't mentioned at all the problem of putting an interaction here. Of course, that's the Kondo problem in the interacting or in Wilson-Fisher model. But I am not going to talk about it. It's more technical. And there is still some story with this double scaling limit and so on. Yeah.
On the form of beta function, how do you see that there are some two zeros, just roughly that you had drawn that?
Yeah. I'll work, if you want, if this is an interesting exercise, we can begin one tutorial session from this action. I'll write the differential equation and show you how to get the beta function from it, including these 3 zeros and the behavior to minus infinity. I just want to go to more conceptual things now. Okay. So I want to begin in the last 10 minutes the subject of Wilson lines. I'll do first, we'll begin with some simple statements on Wilson lines, and then in the next session I'll do 'Hooft lines and S-duality. I'll begin from Wilson lines though. So from now on, we're going to be only in 3+1 dimensions. I'm not gonna be able to cover Wilson lines in 2+1 dimensional fixed points. So the simplest theory to study is, of course, Maxwell theory, which is a nice conformal field theory in 3+1 dimensions. And in Maxwell theory, you can introduce a Wilson line either in the action or as a pass-ordered exponential along the following. Let me just write it more explicitly. It's x and t, d3x, dt. Or you can think about it as this is in Minkowski's signature, or you can think about it as a pass-ordered exponential of iq a naught dt. This is the Wilson line with charge q. So we have to apply the ideas that we've been so far discussing to this problem and try to understand the infrared. In this case, it's of course not a big deal. This is high school material. You can think about it as a localized charge, like a heavy nucleus with charge q under electromagnetism. So what is the saddle point, which is the ground state? What is the saddle point of this system? Yeah, A0 equals e squared q over 4 pi, and then the distance from the defect. Okay, this is the Coulomb law, and it's not gauge invariant, but you can also switch to gauge invariant notation. Of course, you can compute f0i and fij vanishes. This is the usual Coulomb formula, and fij vanishes. So just looking at the powers, this is completely consistent with our rules for one-point functions in SL2R invariant defects, because the gauge field, well, it's not gauge invariant, but let me just be sloppy. This is dimension 2. This will have 1 over x squared. So the gauge field is like a dimension 1 operator, and this is exactly 1 over x. So you can think about the prefactor as the A coefficient in our defect conformal field theory description. So for any q,
But you have a problem with the total energy divergence.
I'll get to it in a second. For any q, this is a SL2R invariant conformal defect. And unlike our pinning field defect, the localized magnetic field, q is not a free parameter. It's not. You should not think about q as an exactly marginal parameter. Why? Does anybody know? Why is q not an exactly marginal parameter? It looks very similar to our integral of phi dt, but it's not an exactly marginal parameter.
Are you quantizing it?
Yeah, because it's quantized. And it's quantized because of gauge invariance. For this action to make sense on a compact curve, q has to be quantized. And in fact, we will compute the g function, the entropy of this defect soon, the g function, and it depends on q. So somehow it knows that q is not an exactly marginal parameter. Okay. Now this is the statement about Wilson lines. There was a question about the infinite energy in a point charge. Remember that for any line defect,
Zohar?
yeah,
If the gate loop is R rather than U1, the Q is not 1, right?
yes,
So how would the entropy argument change?
yeah. Even in that case, Q should not be regarded as an exactly marginal parameter because you are not adding a well-defined defect operator. And the entropy function is smart enough to know about it.
But you can just absorb Q in gate, and it would be together with E.
No, but the deformation, which moves you on the conformal manifold, would not be a gauge invariant defect operator. A0 is not a gauge invariant defect operator.
Locally it's not, but globally it is.
No. So the G theorem only knows about deformations of the defect action by well-defined defect operators. This is not a well-defined defect operator. And I'll give you the exact expression soon, but indeed the logarithm, so the defect entropy of this defect is something like Q squared with some prefactors that I'll tell you soon. So it knows that Q is not an exactly marginal parameter. And it's always bigger than, and it's always bigger than 1 for Q bigger than 1. There is a general conjecture in the literature that the defect entropy of Wilson lines is always bigger than 1. Bigger, let me just try it like this. It's always bigger than 0 for any Q, which is not, for any Q. So unlike our spinning field defect where the defect entropy was arbitrarily negative, this is always positive. Okay, about the energy stored in this system, I gave you a general formula for the energy of any line defect in 4 dimensions. It was something like h over distance squared, and then Tij was something like h times xi xj x squared minus delta ij. This formula was the true expectation value of the energy momentum tensor for any defect. Okay. In particular, this is also the answer for this defect because it's a conformal defect. And what am I doing? X to the 4 and x to the 4. So this is also the true answer for this defect, and this is just the square of the electric field. The electric field is 1 over distance squared. This is the square of that. So the self-energy of any conformal defect blows up, and it's not it's not some special thing about this electric charge.
But you don't integrate over
The fact that
place in the defect, right? Like it blows up in the origin.
Yeah, it blows up. There is a UV divergence in the self-energy of every defect. But why are we not worried about this? We're not worried about it because this is an integral of this form. This is the energy. But this is linearly divergent. It's a counter term. So we just absorb it in the mass of this external nucleus. We know how to absorb this divergence by this cosmological constant term, which is a counter term on the line defect, and it goes away from the defect entropy. That's why the defect entropy is finite, even though there is divergent self-energy.
You can instead use the Born-Infield theory.
The Born-Infield theory is not a conformal field theory, so I don't want to discuss it, but you're right. Yeah.
Again, the divergence is linear?
Yes, yes. That's if this divergence was not linear, QFT would not make sense. The divergence of the self-energy of the electron or any nucleus is like this: d3x over x to the 4, and it's only because it's linear that QFT makes sense. If it wasn't linear, it would mean that you could not subtract it by a local counter term. No, because the energy is integrated over space. Yeah. If this was like 2x, QFT would not make. Oh, sorry. Like, if this was x 4.1, QFT would not make sense. It would mean that you need non-local degrees of freedom in the UV to subtract divergences. Yeah. So I'm not worried about this divergence whatsoever. It's a general property of any conformal defect.
About any case.
Okay, let me now continue to 't Hooft lines. So Maxwell theory has an infinite sequence of conformal line operators labeled by this integer q. It's not known, for instance, whether the O3 Wilson-Fisher fixed point has infinitely many conformal line operators. I've shown you the pinning field, but it's just one. The Kondo problem maybe, well, it depends on the phase diagram, which is not currently known, maybe adds additional line operators. Okay, but this theory also, just for reference, this theory also admits more conformal line operators, which are the Hooft lines, which are functions of some other integer n. And they are defined in a little bit more indirect fashion. So you cannot just write them as a local perturbation of the action in such a simple way. You have to add additional degrees of freedom to describe them. Just to finish, I don't want to go into too much details about it, but I'll just say that they're defined by taking the impurity that corresponds to this magnetic monopole. This is a magnetic monopole of charge n, and so it's defined by saying that the flux of the electromagnetic field is 2 pi n across a small sphere that surrounds the impurity. So you basically remove a ball from space, and you'll say that on the boundary of the ball the flux of the electromagnetic field must be 2 pi n, and you find the saddle point with these boundary conditions. And then you take the small epsilon limit where the ball shrinks. It leads to a conformal defect for any n. And its defect entropy has a similar formula. It's completely conformal, and it leads to non-zero Fij rather than F0i. So we see this infinite set, and we'll discuss it more tomorrow, on Sunday.
Diodes?
Yeah, you can also diodes, yes.